EC 201, lecture 14. We figured out one way in which we could make sure that the bias current through our transistor was independent of the threshold voltage of the device, and we came up with what is called the current mirror, where we assume that the transistors M1 and M2 are identical with respect to mu and Cox and Vt, and the input was added on like this. And both these were infinite capacitors. Okay, in case you are confused about this circuit diagram, this is exactly the same thing that we drew. It's just the transistors moved around a little bit. That's all. It's electrically the same circuit diagram. Is it clear? Alright. So, this transistor is used to figure out the answer to the question, what VGS must I apply to the device in order that the drain current is IREF, and whatever voltage VGS1 is developed between the gate and source is applied to M2, and by virtue of the fact that M2 is identical to M1, the drain current in M2 is going to be exactly the same as that in M1, which is IREF. Does that make sense? One could argue that this is a technique that's only appropriate for an integrated circuit, because when you're doing discrete circuits, if you buy two nominally identical FETs from a market, you will find that the thresholds are different, and so is mu and Cox and so on. Okay, so there will be slight differences. So if you use this particular arrangement, because M1 is not exactly equal to M2, you can expect that there is a fair amount of difference between the drain current of M2 and the drain current of M1, which is IREF. The question now is it possible to do the same kind of approach where the bias current is independent of the threshold voltage of the device, but use only one transistor? So here we have one transistor which is used to figure out VGS1, and the other transistor which is actually doing the amplification. Correct? Is that clear? Which of these transistors is used to figure out VGS1 and which of them is doing the amplification? M1 is figuring out VGS1, M2 is doing the amplification. The question is, can the same transistor be used to do both? So we all agree that this bias arrangement will exactly figure out what VGS1 you require so as to have IREF in the drain of M2. But we want M2 to amplify also. So while for DC, so the circuit must look like this for DC, and how must it look for AC? For AC we need the small signal equivalent when you add on the source to look like, correct? So we need, in other words, to cook up a circuit which looks like this for biasing purposes, and one which looks like this for incremental signals, perhaps with some resistor there, because if we look back at yesterday's notes, we found that it's not just RS but also some resistance RB. And this RB was not peculiar to yesterday's circuit. Even the very first circuit that we had RA parallel RB being the equivalent RB. So any suggestions on how I might be able to realize such a circuit? Pardon? Somebody says I need a capacitor at the gate. Why would I need a capacitor at the gate? So adding on the source and the load is actually quite straightforward. Once we figure out, the load can be added on to the drain in a very straightforward fashion. Correct? It's simply, for example, if I did this, so if I hooked up a circuit like this, what could I do to add input signal to the gate? We do what we are used to, which is put a large capacitor, RS, Vs. How would we add on the load? Parallel to? see this part, I mean imagine you are in the lab, right? You put IREF, you take M2, you short the drain to the gate, and you are all set as far as the quiescent signals are concerned. Correct? You have done the quiescent part. Now I need to make this chap here look like this guy for incremental signals. What all is there in the incremental part which is not there in the quiescent part? First is the input, of course, and that's done in a quite straightforward manner. We are now used to this standard trick, which is RS, Vs. Okay? What else is there? There's RL. That's also quite straightforward. Okay, now what is the only thing that is missing between, are we done or? Pardon? RB is straightforward to add, right? I could, for example, RB, please notice, was something that was not desired but was coming because of the way we bias the gate. If you want to split hairs, sure, I can add RB here. Alright? I could choose RB to be infinity, in which case this will go away. So am I done or is there something I'm missing? What is the incremental gain of this circuit? Okay, I claim that I'm done now, my amplifier is working. Any comments? Why? Okay, how many of you smell a rat here? Yes sir, why do you smell a rat? Yes, so you can clearly see that this is a problem. If I drew the incremental equivalent of this chap, now how will it look? This part is okay, this part is fine, so is this part, okay, but in the incremental equivalent we want gain, we do not want what is there in the bias circuit now that prevents you from getting gain? The drain and the gate are shorted in the bias circuit. If you did that, now the AC gain you will get is, it is not 1. It is not RL by RL plus RS, okay, tempting though it may sound. So what is the incremental equivalent of this transistor when it's connected like this? We saw this yesterday. Yeah, it's a resistor of value 1 over Gm. So what is the gain? Somebody quick. See, when a transistor is connected, the drain and the gate of the transistor are connected together and the transistor is operating in saturation. The incremental resistance, equivalent circuit looking in at from the drain is simply a resistor of value 1 over Gm. We saw this in the context of the bias circuit yesterday. Alright. So if this is 1 over Gm, it is M2 for incremental signals behaves like a resistor of value 1 over Gm between the drain and ground. So not only do you have RL, but you have 1 over Gm in parallel with RL. So the incremental gain is RL parallel 1 over Gm divided by RL parallel 1 over Gm plus RS. Does that make sense? Okay, those of you who are not yet convinced, please work it out. As I said, there is no trick, there is no rocket science, okay. The procedure is straightforward. You find the operating point, then replace every transistor by its incremental equivalent circuit. You replace, every infinite capacitor by a short circuit, every voltage source by a short and the current source by an open, and solve the linear network. That's all there is to it. There's no need to guess, there's no need to remember or mug up, for that matter. Great. So, we all realize that the source of the problem. The source of the problem is, why is this not giving you any gain? Because the drain and the gate are short. So, any smart engineering solutions to this? One good solution, though not practical, is to have, so why do you say inductor? Just like an infinite capacitor charged to a voltage V is indistinguishable from a battery of voltage V. By the same token, an infinite inductor charged carrying a current I is indistinguishable from a current source of value I. Does that make sense? One suggestion is to put an inductor there, an infinite inductor. What is the DC current flowing through the inductor? Why is the inductor current 0? The inductor is a short circuit and no current flows through the gate. So the inductor current is 0. So when the inductor current is 0 and it's an infinite inductor, it is equivalent to a current source of value. An infinite inductor carrying a current I is absolutely identical to a current source having a current I. In our particular case, the inductor current is 0. So it's like having a current source which is 0, which is equivalent to an open circuit. Does it make sense? So this is one solution. It's a good solution. It is not quite practical simply for the reason that it's hard enough to get infinite capacitors, okay, and getting infinite inductors is actually turns out to be a very difficult proposition, okay. So if one does not have the freedom to have infinite inductors, can somebody suggest a workaround? And what is the drop across the inductor? You want basically the DC drop across the inductor to be 0. I mean across whatever you put here, across this element, you want the DC drop to be 0. But whatever element you put there, as long as there is a conducting path from this node to this node, since no current flows through the gate, what will be the drop across this element? Okay, for example, if the inductor was, let's say the inductor had a resistor in series. Okay, what happens? Does something change now? You had an infinite inductor in series with a resistor. What happens? No current flows through the inductor, everything remains the same. Okay. Now let me make this a very, very large resistor. Does something change? There is no change. Why? Because there is no current through the inductor is an open circuit, blah blah. But is this a better open circuit now, or was this a better open circuit when R large was not there? It is true, both of them are open circuits, okay? But it's like saying everybody is equal, but some are more equal than the other. Huh? Obviously, when you add the resistor in series, the quality of the open circuit you get is a much better open circuit than with the inductor. Okay? And the large resistor doesn't need to bother us because there is no DC current flowing in the resistor anyway. So the next logical step is to say, to remove the inductor because the inductor is difficult in the first place. This is simply a workaround because an infinite inductor doesn't exist. Okay? Even a finite inductor is quite problematic, especially in the context of integrated circuits where inductors can become, even nanohenry inductors can become very, very large. So what is the modification I need to make in the incremental circuit now? Put a large resistance between the gate and the. So let's quickly analyze the gain of this amplifier. Do this for the special case of RS equal to 0, simply because it's easier for me to work out. You can actually do the one with finite RS, you know, when you have the time in the room. How would I figure out the gain? No, for DC, how does this look? What is the equivalent for DC? These capacitors go away. These go away. And for DC, what all that you have is Iref. Okay, for DC, what do we do? There is nothing flowing through the capacitor, so I get rid of this guy. Similarly, the source goes away. This is what you are left with for DC. So, is there any drop across R large? We want this to be an open for incremental signals. For incremental signals, you want this to be open. That would require an inductor. But an inductor is not practical. So you have to do with what you can do, which is put a large resistor. Now the obvious question is, what is large? Correct? That will become apparent the moment we find the gain of this amplifier. But is this clear to everybody? That adding a large resistor between the drain and the gate does nothing to? You don't understand? Okay. Okay, all of you understand this part, right? Do all of us agree that the voltage developed here will be VGS1? And why is this VGS1? So basically we are comparing ID with IREF. If ID is smaller than IREF, this node potential will go up, okay? And which means that the VGS we had applied was too low, which means you have to push VGS1 up. And since VGS1 has to be pushed up, one could directly connect X to the gate. Alright? Does that make sense? Since the gate doesn't draw any current, it doesn't matter if I connect X directly to the gate or X through a resistor to the gate. The gate doesn't care because it doesn't draw any current anyway. So in other words, whether we had the circuit yesterday where there was no R large or whether you put an R large, the bias conditions remain the same. Is everybody convinced now? There is nothing large or small in the world. Everything is relative. So it makes sense to figure out what is R large. So the thing is to find the incremental gain of this amplifier. What should I do to find the incremental gain? I replace the transistor by its incremental equivalent circuit, which is simply, so this is GM, if this is Vs, this is GM Vs, and this is Vout. Can you guys help me figure out what the incremental gain is? I write Kirchhoff's current law at the output node. So Vout minus Vs times G large, where G large is the conductance of R large, okay? That's the current flowing through R large, plus GM times Vs plus Vout times GL must be equal to 0, which means Vout times G large plus GL must be equal to minus GM plus G large times Vs, which means that the incremental gain Vout by Vs is minus GM plus G large divided by GL plus G large, and this can be written as minus GM by GL, so 1 minus G large by GM divided by 1 plus G large by GL. And what minus GM by GL? This is what the gain we would get when we had the original circuit without R large, okay? And clearly, what do we see? The gain is now, is it smaller than before or larger than before? It's smaller than before. So what is, when you say the resistor must be large, how should I choose that resistor? G large should be very small compared to, think carefully, which do you think will be larger, GM or GL? Any comments on whether you want GM to be large or GL to be large? I mean, comparatively, which is larger? GM, because you want gain. Okay? So, if G large is much smaller than GL, then it will be automatically much smaller than GM. So, when we mean R large must be a large resistor, it must be much larger than RL. Alright? So, which means that if you choose R large to be much larger than RL, then the gain is approximately minus GM RL. Does that make sense? So, you have therefore seen that in this way, you use the same transistor to fix the VGS in such a manner that the drain current remains constant and equal to IRF regardless of the value of the transistor threshold. Does that make sense? So, you can see that there are any number of ways of getting the same incremental circuit. Alright? The real circuit can look very different, but the incremental circuit can be the same. So, there are many circuits which will have the same incremental equivalent, and you already seen three. The first one being the gate simply being biased by a string of resistors. Alright? This is, I mean, you've seen the first circuit where RA and RB were a resistor string. You've seen a second example where we use a current mirror. We've seen a third example where you can do what the current mirror does equivalently, but use the same device. So, can somebody comment on the swing here versus the swing in this current mirror case? Where do you think you'll be able to swing larger? The gain is the same in both cases. If RL is sufficient, if R large is sufficiently large, the gain is the same in both cases. Okay? Do we have any? I mean, when we wanted to maximize swing, what did we do? Okay, why is the swing constrained? What determines the largest amplitude of the input sine wave we can put in before the output starts to clip? Pardon, on one side it is the transistor goes into the triode region, on the other side it gets the transistor gets cut off. The cutoff limit is not dependent on is only dependent on the quiescent current of the MOSFET as well as the GM of the MOSFET. Okay. On the other hand, the limit of the triode region is dependent on Of course, it depends on VGS, it depends on VT. What else does it depend on? Triode operation is defined as what? That if the transistor has to go into triode, the drain has to go below the gate. So obviously the limit better depend on both the quiescent value of the drain as well as the gate. Okay. So in the circuit with the current mirror, was there any freedom in choosing the drain quiescent voltage? How can I change the quiescent voltage in this circuit at the drain? How can I change the quiescent voltage? What determines the quiescent voltage at RL? The drain of M2? ID, okay. It's VDD minus ID RL. ID is presumably fixed. So there are a couple of ways of varying the quiescent value. One is to vary the VDD, or if the VDD is fixed, one can vary RL and take the change in the gain that you get. Okay. But the key point to notice is that there is a lot of freedom in choosing the VDS of the device. So can you now look at this circuit and tell me, comment on the VDS of this device? What is the VDS of this of M2 in relation to VGS? It is exactly the same. So obviously, once you have chosen VGS, which means once you have fixed I or Iref, the VGS and by way of topology the VDS are both fixed. Okay, so this again drives home the point that there is no free lunch. We thought we got rid of one transistor, but this is imposing certain other constraints. So the output swing of this amplifier can never exceed how much before getting cut off? If the gain is large, the voltage at the gate is the swing at the gate is much smaller than the swing at the drain. Is that clear or it's not clear? We saw this before. If the gain is very large, the output is much larger than the input, which means that a small swing at the gate will result in a large swing at the drain, which means we can do an engineering approximation say the gate doesn't move, it's only the drain which is jumping around. And how low can the drain go before the transistor gets into triode? It can go 1 VT. So definitely in this amplifier, the output swing can never exceed VT without the transistor moving the triode region, which will cause the sine wave to distort. Okay, which side of the sine wave will get clipped off? The top or the bottom? The bottom of the sine wave. You understand? So these were two instances of using negative feedback to stabilize the operating point of the transistor, where stabilizing the operating point basically amounts to making sure that the drain current of the transistor remains fixed regardless of what happens to the threshold voltage. Alright? And the basic idea is the following, which is measure the drain current, okay, and compare with a reference, okay, then if the drain current is greater than Iref, what should I do? If drain current is greater than Iref, decrease or reduce VGS. Okay. If drain current is less than Iref, I must increase VGS. This is what we saw yesterday. This is common sense. Okay. Okay, how do we get a current source? For the time being, assume that it's a given. All right. It turns out that there are ways of generating current sources using transistors. Now that you already know how a transistor works, if I had a stable voltage source, for instance, I could apply it across the gate source of a transistor, and then the drain current will be a current source. Okay, that's one way of generating it. That's a very cheap way of doing it, right? And it's a bad way because the current will keep varying when the threshold changes. But there are lots of ways in which you can get rid of all these things. But for the time being, you assume that a current source is God given and exists just like a voltage source is God given. So everybody understands the basic idea, right? Okay. So let's see how many ways there are of exploiting the same basic idea and generating several circuits which all look very different but still exploit the same basic idea. One observation is that the gate current in a MOSFET is 0, right? So the drain current is the same as the drain current is equal to the source current, because the gate current is 0. By Kirchhoff's law, whatever goes in must come out, so ID must be equal to IS. So yesterday we had this thought experiment where we'd go to the lab, hook up the transistor, the drain connected to a sufficiently large potential to ensure that it is in saturation, okay? and we put the ammeter in the between VDD and the drain. But I drain is the same as I source. So there is nothing preventing we could have put the ammeter in the source. So you can either measure current in the drain or current in the source. Okay. You compare with the reference. If the drain or source current is greater than Iref, you must reduce VGS. On the other hand, if the drain or the source current is less than Iref, then you must increase the VGS. Correct? In other words, okay, so this is ammeter VGS, and this is what you are varying. Yeah, what is the voltage drop across the ideal ammeter? 0. All that I am saying now is, I could have as well put the ammeter in the source, and nothing would change from yesterday. I mean, right, the way I would go about finding VGS still remains exactly the same. So this is current measurement in the drain, this is current measurement in the source. Alright. So these seem to be two ways of measuring the current of the quiescent current of the transistor. Alright. The next thing is, we need to change VGS. How many ways do you think there are of doing this? So you can change VGS by, yesterday what did we do? The source was grounded. We changed VGS by yanking the gate up or down. That's what we did yesterday, in case you don't remember. In how many other ways can you think of? You can change VGS by keep S fixed, the source potential fixed, and vary the gate potential. Alright, now extensions. You keep the gate fixed and do what? Vary the source. Is that all there is to it? You could vary both at the same time. Okay. So if you insisted that one of the terminals remain fixed, there are two ways of varying VGS, and there are two ways of measuring current in a transistor. So which means how many circuits will come out? 4 circuits come. What we did yesterday, which is this way of finding VGS1, corresponds to the case where current is measured in the drain and VGS varied by keeping S fixed and yanking. So we look at the other cases.